Okay, let's see. I'm going to do a little videos for these notes too. um, so this whole section is on ideals and actually a lot of stuff in this section. So I say ideals and homomorphisms, but this actually covers most of the rest of what we do in the text. To some extent, just not quite concentrating on polynomials as much as the text does. Um, that's me. I like generalization, so I like to be as general as I can and then just apply the general theorems. But anyway, let's start with ideals, and then we'll look a little bit at homomorphisms, and I'll see how many of these videos I make here. So I'm going to do one video for ideals, video for homomorphisms, and then I'll keep seeing how many I want to do. So just to remind you, let's see. So, I mean, we've had a couple of different kinds of algebraic structures so far. We've had groups, where we may have a structure like that, or we may have a structure like this. Or we may have a structure with some other operation, G, maybe it's star, could be composition, whatever it is, right? And E, right? So we've seen all sorts of groups. We have now rings, right? So rings, here we have plus and times, and we always have a 0, okay? And that's pretty standard notation for rings. Groups have all sorts of notations, but this is pretty standard for rings. Sometimes we have a 1, right? And I'll talk about this a little bit more later, but if we actually consider the 1 as part of the structure, then we're actually looking at unitary rings, and that's a different category of structures. And you may have other things too. I mean, with matrices, you could have two different kinds of multiplication, right? You could do like the element-wise multiplication, and you could also do matrix multiplication, right? And with spaces of functions, you could do element-wise multiplication, or you could do composition again, right? So matrices and functions kind of are similar. So you could have even more general algebraic structures, right? So the theme we're talking about here is very, very general. It works for all sorts of algebraic structures, not just rings and groups, but vector spaces and modules and all sorts of things, right? So I want to just say a little bit about that, and this should be review in a way, and I'm going to focus specifically on this case for rings. Just keep in mind that everything I'm saying is pretty general here. So one thing we want to do, and we've seen it used a lot in groups already, so I don't really have to justify it, is we want to define a kind of relation on R, and it's going to be called a congruence relation. One of these days I'll learn how to write. And it's an equivalence relation, right? So if we take R and we view R as a blob, right? Then equivalence relation, splits R up into equivalence classes. Now R is a group among other things. So you know that one of these equivalence classes is really important, namely the one that corresponds to the additive identity, right? So let me just pick a spot to put that one. So I'll put it over here to the side. Maybe I'll put it here, right? So let me just color in this one right here. So this one here, this will be the class corresponding to where 0. So 0 is in that class, right? So we've taken it, we partitioned it, right? That's what an equivalence relation does, right? So 2 points are in here if they're equivalent to each other. Or you could have the partition and define the equivalence relation as two things are equivalent if they're in the same piece of the partition, right? And this little part that has 0, and then just to get the notation going, we have A, which is an R. And so I could write the equivalence classes that, or I could include the little squiggle down there to make the relation specific, or I could write it like this, right? It's sort of a mod out type thing. Lots of what we do today will actually have things we're writing. Well, let me stick to those for right now. So the class with the 0 in it, right? So this is the 0 of R. Okay, so I will not write this little subscript most of the time. Would be the class with 0, right? And we know that this is a subgroup, right? So we know it's a subgroup of R plus 0. I mean, we know that's what we want. And in fact, well, yeah, I mean, so we know that's the sort of situation we're in, or that's anyway the kind of case that we're considering. And what we want is we want to be able to take different classes, so here's maybe the class with A in it. Here's maybe the class with B in it. Not that you can read that. I'm not sure how to make that readable. like A is there, B is there, right? Right, and I want to like sort of take the algebra of R and make it work on these classes, right? So I'd like to define like A, B, right? In fact, let me just be a little bit more formal for a second. I like to define something like A and then times in the sense of R twiddle B, right? And I would like to define this as A times in the sense of RB, right, class. So I'd like the classes to behave nicely. Same with plus, right? A plus in the sense of R twiddle, right? So this is the quotient structure, right? B should be A plus RB, right? And so we're hoping that the algebra all works nicely with the classes, right? Maybe we get a ring, a group, whatever it is we want, right? So we know to get a group, what we need to have happen is we need the zero class to be a normal subgroup of the additive group part of the ring. And okay, normality is actually, we don't really need to say normality because it's an abelian group, so it's going to automatically be normal, right? So we just need a subgroup, right? So that'll give us the group structure. And then we also want to sort of get the multiplicative structure too, right? And then we want to show it's a ring and all that sort of stuff. So there's lots of little steps here, but that's kind of the idea. But the main point I want to make here is the idea is you have an equivalence relation. It breaks your structure up into classes, and you want to try to define an algebra, same kind of algebra using the operations from R on the classes, right? So that's the idea, right? That's a pretty easy idea to understand once you've done it enough, right? I mean, it's a common thing to do. So let's see. In the notes, I say a few more things. So the zero, right, should be the zero class, right? The zero of the quotient structure should be the zero class. Let's see. I'm just saying the same things. If we had a one, right, then the one. Then this class with the one of the ring in it would be the one of the quotient structure, assuming all the algebra is working, right? So that's good, right? So that's the general idea of congruences. We start with an algebra, we define some sort of relation on it, and we try to extract a new algebra, which we call the quotient algebra, which should be again in the same kind of algebraic structure, right? And so formally in math, we would say in the same category of algebraic structures. So we'd like to take the quotient of a group and get a group, right? We even have the category of abelian groups, right? So we take the quotient of an abelian group and get an abelian group. We take a quotient of a cyclic group and get a cyclic group, and things like that, right? So just like with groups, we didn't really focus on the equivalence relation. We focused more on the subgroup, right? So we want to do the same kind of thing with rings. Now, this doesn't always work with all structures, right? This is something a little bit special to this kind of structure. Maybe a structure where it wouldn't work at all would be like if we wanted to do quotient graphs, right, or something like that, where you didn't have a zero kind of thing, right? So I want to characterize like what is an idea. So what do we want? Like, I guess what I'm going to do is I'm going to look at what properties does the zero R have, and I want to extract from that. Sorry, that's not what I want to say. What properties would the zero of R, this class, have to have, right? So we know it's a subgroup. We know that from the stuff we've already done with groups. And I want to look now at the multiplicative part. And what we see here is this has to happen, right? If I take an element R and I multiply it in this sense, right, with 0, right? And if things are working out nicely, well, this should give me R times 0. No, yeah, let's see. So I'll keep writing 0R. I'll probably stop writing, but notice I'm dropping the subscripts on the different multiplications. Okay, but this is clearly should be the 0 class, right? And going from the other side, you get the same thing. That should also be the same as this class, because 0 times R is R times 0 is equal to 0, right? And so this should be the same as this class. So we should have this kind of thing happening. Okay, now let's think about what this says in terms of this specific kind of structure. So one thing to keep in mind is we're using the, this is a a group, I'm going to just call it I, okay, for ideal, right? So I'm going to concentrate on this class, right? And for a moment, I'm going to call it I, right? And so R is, so this class R, right? Again, we're in the additive case, so it's R plus I, right? This is just the structure we would do to, this is the, you know, left, left, I'm forgetting the word, right? Sorry, you know, like we have a subgroup and we have AH coset, right? It's like the left coset. Okay, but we're in a commutative case, so left and right cosets are the same, right? But we're using the additive notation, so we have plus and not times, right? Okay, and so so that's R, right? And then zero, so the zero R class, right, is really just 0 plus I, which is really just I, right? So it's like that. On the other hand, it's really also S plus I for any S which is in I, right? It doesn't matter which choice we take there, we get the same class. So this thing I have written up here, I'm going to just concentrate on the first row of it, actually, that row right there. So I'm going to rewrite it like this. This I could write as R plus I, and then S plus I, because I'm going to take an arbitrary representative of the class R, an arbitrary representative of the class 0R, right? And what I need to have happen here is I need this class to just be I, right? That's what I want to have happen, right? So let's actually do the work here. So this is, you know, this is RS, right? How do I want to do this? Sorry, let me think for a second. Maybe, okay, let me spell this out. Yeah, okay, fine. So let's, I want to look at it. I want to show that these are this. I want to sort of think about when these are the same. Sorry, that's what I want to, I want this to happen, that these are the same. Yeah, sorry, for R in R and S in S, right? Sorry, in I, right? So let's see. So let me be a little bit more careful about this, right? So this is what I need to have happen. Okay, so we're going to do this as sets, right? So I'm going to take a thing in here. So this will be of the form R plus, let me call it A, okay, and this is going to be S plus B, right? So I'm taking just a thing from in there and a thing from in there, and I'm multiplying them together, right? So now I can use the usual algebra, and so I have RS. I don't have commutativity multiplication, right? So you want to be a little bit careful. Plus RB, just using distributivity, plus AS, plus AB, right? That needs to be an I, right? So that's a thing that I need to have happen there. So I guess initially I'm focusing on just what do I need to have this part happen, right? So that's sort of what I'm focusing on. And so in particular, what I need is so remember this we know is already a subgroup, right? So I need, for example, so this is an I, right? Because that's just, actually, no, it's A and B. No, actually, we don't know that either. Okay, we don't know that either yet, right? So I need all of this stuff, right? I need all these things to be an I. So this needs, whoops, this needs to be an I. This needs to be an I. I mean, if all these things are an I, right? Then I certainly get this subset relation. That's kind of the thing I'm focusing on, right? And so sort of what does that mean? Well, R is coming just from the ring, B is coming from the ideal. So this is something from the ring, something from the ideal needs to be an I, right? This is something from the ideal, and oh yeah, and then S, right, which is also something from the ideals, right? So that needs to be an I, and then A, this is supposed to be A times B. God, I'm so sloppy. Okay, RS, RB, AS, AB. So this is messed up here. I just need to slow down. These are all supposed to be an I, right? So A, S are two things from the ideal, because remember S was from the ideal, right? A, B are two things from the ideal. So these is from the ideal. From the ideal, when I multiply them together, I want them to be in the ideal. RS needs to be in the ideal, right? And RB needs to be in the ideal, right? So anyway, all these things need to be in the ideal, right? So that would certainly all be true if it's the case that R, I want to write it like this. I'm just going to write it like this. Ri, right, is contained in I, right? So in other words, anything from R times anything from I ends up being an I, right? So that would make all of these multiplications here in I, and of course I is a group, so when I add them together, it stays in I, right? It's closed under addition. So that's going to be a condition we take, right? So in order for the algebra to be working out, certainly this line up here, these two lines need to work out, right? And for those two lines to work out, it's necessary. I haven't shown it's sufficient yet, but I'm showing it's necessary that this holds, right? If you concentrate on this other side, sort of the right-hand side of this thing, you get the opposite part of this, and you get that IR has to be contained in I. Okay. So these are the two conditions we're going to focus on now, right? So I'm going to say I is an ideal, if and only if. So 1, I together with plus and, well, I is a subgroup, right? Just as a set, it's a subgroup. So I is a subgroup, just write like this, of R plus 0. Note that in particular, I mean 0 is in there and it's closed under addition. It's a subgroup, so it's also closed under additive inverses, right? And then 2, I want to say that I can do this in one thing, union Ri is contained in I, right? Let's see, is there another way I could do this? I could just say, no, I guess that's how I need to write it, right? Notice that with this, it's clearly the case that I, because I is a subset of R, so I is also contained in I, right? So in particular, I is closed under multiplication as well, right? So we could change this a little bit and change it to 1 prime. I is a subring of R, right? So in other words, it's got 0 and it's closed under the operations plus and times, right? And then 2 prime, we still need this condition here, right? That Ri union IR is contained in I. Okay. So just a little comment here. This is called a two-sided ideal. I could just assume Ri is contained in I, and then I would get a left ideal, and I could have IR is contained in I. I could have a right ideal. I mean, there's lots of things you could do here, right? But we're always going to be interested in just ideals, which are two-sided ideals. And obviously, if the multiplication is commutative, then all ideals are two-sided ideals, right? So this is kind of the typical way we think about this, but either one of these two things, right? It might be easier to prove that something's a subgroup and then and we have to show the stronger closure anyway, so maybe that saves a step or something. So now we want to turn this around, right? And what I want to say, oh, and here's another important thing, right? Generally 1, so let's say we're in a ring with with unity. So let's just notice this: if 1 is in the ideal, right, then the ideal has to be all of R, right? And why is that? Well, because if 1 is in the ideal, then R times I, will contain R times 1, right, which is R, right? So when we're talking about ideals, we almost always really mean proper ideals. We almost always mean 1 is not in the ideal, right, for a proper ideal. So that's really, really important because that's part of the reason we need to talk about rings without unity anyway. If we want to say this is a subring, right, then we definitely need to be talking about rings without unity in order for ideals to be subrings. And so that's part of the reason the language is the way it is. Okay, so now we take this as our definition, right? So now we have a definition. We have a ring. I is contained in the ring, right? I is an ideal. If and only if. So 1, I'm just going to do the group version. So I is a subgroup, of R plus 0 and 2, IR union RI, is contained in I. Remember, this is just a shorthand of saying IR is contained in I and RI is contained in I, right? So that's what we're going to mean by an ideal, okay? And now let's think about, so given an ideal, right, we know that we have a subgroup, right? So we know we have this quotient group structure anyway. And remember that the way we would write things would be R plus I, right? That would be the typical, this would sort of be the equivalence class of R, right? And the corresponding equivalence relation, which we could call squiggle I, right, would be R squiggle IS if and only if R minus S is an I, right? So again, this is just going back to our group stuff, using the fact that we're in a Abelian group using additive notation, right? So it's good to just, sort of keep this stuff in mind. And what I want to do now is I want to show that the quotient structure, okay, we know that this is an equivalence relation. We know the quotient group structure is a group. We already know that, so we don't have to do that. So I want to show that the quotient structure R twiddle is a ring. And I'm not sure I'm gonna, well, yeah, okay, let me see what I'll decide to do here. Maybe there's only so much time left, so maybe when it stops, I'll quit. But the main thing I want to do is show that multiplication is well defined, right? So remember, I only had like the condition being a sufficient condition. I want to now kind of turn it around and say, if I have a set that satisfies the condition that it's kind of got this strong, two-sided closure, right? Then what I get out of this quotient procedure is in fact a ring, right? So I want to show that multiplication is well defined, right? So that's the main thing. And then you want to show distributivity and other stuff, right? But what I want to do right now is just show that it's well defined. So I want to say that sorry, let's do it like this. Let's use this notation. So doing R plus I, S plus I equals RS plus I, right? Is a well-defined definition, well-defined operation, right? I'm defining it on the quotient structures, right? It needs to be well-defined. So what do I mean by that? I mean that if R plus I equals R prime plus I and S plus I equals S prime plus I, then RS plus I equals R prime S prime plus I. That's what I need to show that it's well defined, right? It doesn't matter what choice of representatives I use, I get the same, well-defined product, right? So let's convert this into what it means for, so R plus I equals R prime plus I means that R is equivalent to R prime, right? So we could write R minus R prime is in I, right? And S minus S prime is in I, right? Then I want to know that RS minus R prime S prime is in I. Okay, so this is what I actually need to show, right? Now this is just turning into algebra, which is good. We're in an algebra class. And let's see if I can do it without looking. So I'm going to do a fairly standard thing and just add and subtract zero. Well, I'm going to add in zero, but I'm going to do it by adding and subtracting something. And I don't really think it matters what I do. So I'll do RS prime plus RS prime, right? Minus R prime S prime. So this is the same as RS minus, because this is just zero stuck in there, right? And then we'll do some factoring where we can. So this is RS minus S prime. This is plus R minus R prime S prime. Now you have to be careful. You need to not use commutativity by accident, right? But this is equal, right? And then what do we have here? Well, this thing by assumption is an I. And this thing by assumption is an I, right? And this is now something in R times something in I, and something times I times something in R, right? So we know this thing is an I. That's the strong closure condition we had, right? So this is telling us that the multiplication is well defined, okay? And then showing that it has the right properties, distributivity is really the main property here. Proving that would be kind of similar, right? It's the same kind of thing. So I think, yeah, I think that's all I need to say for this section.